Okay, so my name is Jimmy. You can find me on Twitter at jbogard. My GitHub has a lot of interesting and non-interesting stuff. You can find it at github.com/jbogard. I blog sometimes on Los Techies, and most people either love me or hate me for AutoMapper there. So I work at a company in Austin, well actually out of Dallas as well, called Headspring, and we do a lot of custom app development. And most of the work that I actually see on a daily basis is where a company has an existing product or an existing solution that they had for years and years and years. And what they want to do is replace that existing legacy something with something better. I usually get called after like the second or third time they've tried to rewrite it themselves and had some failure. Usually they call the project like Project Phoenix. Does anyone here have a Project Phoenix right now? Okay, or Next Gen. It's either Next Gen or Project Phoenix, and I get so excited when I see yet another Project Phoenix out there. It's rising from the ashes. Except they don't know that the Phoenix is already dead and is still waiting to rise from the ashes again. Anyway, so a lot of what I deal with is existing systems. And one of the reasons why rewriting legacy systems fails is because it's very hard to actually replace a legacy system that's being used today. You can find examples of this. I actually drove it from Austin, and they're actually replacing the entire highway all the way from Austin to Dallas. It's like 140, 150 miles, something like that, of highway. They're replacing the entire thing. So the way they do this is they don't shut down the entire highway for 3 years while they rip everything up and build a new one. They can't do that because people are driving on it while they're going. So instead what they do is they replace a little at a time. So a lot of what I do is have to try to replace existing legacy systems a little at a time. And this is where we start to enter like the difference between the ideal world versus reality. The ideal world of systems that we would probably all like to work on is something like this, where it's like a pristine environment, the sky is blue, all the highways go exactly where you want it to, and there's like some dude over here with a jetpack for some reason, I don't know why, but it's very like futuristic, everything is exactly as it should be and where it's supposed to be. But the systems that we actually deal with look more like this, the slums from District 9, where there's like aliens there that eat cat food or something, I don't even know, it's really weird. And it's not exactly where we want it to be. So the idea is to try to take this and do something like that, and not have everything go down in the process. So a lot of what I deal with is a lot of old existing systems where we're trying to take that existing solution and platform and modernize it and bring it up to at least something more recent. Maybe the last 5 years would be nice. This will be basically going through a bunch of different examples of crazy systems I've had to deal with and how we've used InService Bus to both help stabilize the existing system and help bring it into the modern world. The first one I was working with, my actual first real system I'm working with InService Bus on, was a system where originally when I came in, it was a bunch of back-end batch processing programs. So like every once in a while, these systems would come online, a batch job would execute, do some work, and then go to sleep again, which using the Windows Task Scheduler wasn't too horrible, but once we got about 60 or 70 of these things, each with different like startup times and different periods that actually run, it just became an absolute nightmare to work from. And one in particular where we were working with was a system that was an AS400 mainframe. Does anyone know what an AS400 mainframe is? That's way more than, that's depressing. But these things are powering like so many businesses. In fact, if you went across the street to the mall, you'd probably find a lot of these AS400s actually out there. These things are used a lot in the retail world to power all those point-of-sale machines. And they work fantastically. I mean, they're super reliable, and they're very simple to work with. They're just kind of old technology. And so this system, what we were working with, needed to get some information out of that other system. And of course, it being an AS400 mainframe, the best way to do so was to just have file exports that we would consume. And one in particular what we were trying to do was, this was in support of an actual retail chain, and a customer complained like, I bought something and something was messed up. And so our system only got the SKU numbers of the things, and so we couldn't actually see what the customer actually bought. So we said, hey, can we go ahead and get your product catalog to let us know like what the actual name of the product was so they could better help on the phone to figure out what actually went wrong and say, oh, actually you did buy this thing or whatever. So we said, that's great. Here's our product catalog. And it was 140 megabytes of just raw CSV data. So we thought, okay, that's cool. We can go ahead and just put that in our database. And then if every day, if something changes, can you go ahead and give us that delta? And they said, no. we can give you the whole thing every single day. And that's exactly what they did. It was a once-a-day dump of their entire SKU catalog with a single flat file that had about 1.4 million rows, and it was every SKU they had ever sold ever. So we saw products in there back into the 80s of things they hadn't sold in forever, but they didn't have a way to filter it out, so they said, just here's absolutely everything, have fun. And what we were trying to do is take that file and get it into our system. Now, a lot of our system, when I first came on, the way we would handle these sort of files was we'd have some sort of batch job, like I mentioned before, that would read the data out and then insert it into the database as a single, basically a for loop. For each row in the file, insert something to the database, and then commit it when you're done. So that works okay if you have a few rows in there. If something happens, then the transaction rolls back, but then I don't actually know what succeeded or what failed in those situations. So we just actually retry the entire file. That's not horrible if you have a file of 10 lines or 50 lines. But over 1 million lines and trying to go through the entire thing all over again is just an absolute mess. And also, the other thing we saw is that it would open the transaction across the entire file. And so that's a pretty big transaction to have 1.44 million rows in your database in one single transaction, just absolutely insane. So we stopped doing that for nearly all of our file processing in our system, which that's what it mostly was. Oh, by the way, we couldn't do anything like an API call or web service or anything like that. Trying to hook up a web service to a mainframe is generally a bad idea, so don't do that either. So we changed this. We changed this into a two-step process where the file coming in, the very first step what we would do would be notified in an NService Bus host that would first take that file and parse it out where each individual line was an individual message. So the transaction was still somewhat large. Sometimes we would have 1,000 or 2,000 messages just sort of hanging out in an MSMQ transaction, but it still performed pretty well. And the other thing we found was by taking each individual line and making a message out of it, then I can reason about the success or failure of each individual line in that file as individual transactions. So when that transaction committed, we would have all these messages go to a separate host, which was our actual processor, to process all the individual data. Each individual message would go through the normal NService Bus pipeline. So if an individual line in the file failed, it would retry that one single line. If it failed too much, it would go to FLR's SLR and eventually an error queue. So we didn't have to worry about things like someone accidentally hit the comma or in the file and screwed up the processing for the entire file. Instead, we would just have that one message fail that we could retry at a later point. So that's what we did for nearly all the files in our system, except for this one, which was 1.4 million lines. Real quick to show you what it looks like in actuality, what we would do is we would read all the lines in the file. We would create messages that represented each line, and then for each line, we would just go ahead and do bus.send. Then actually processing the line, we try to make this as dirt simple as possible and shield your eyes. This is ADU.NET code because there was no reason for us to bring an ORM to just do an insert. So this would just take whatever data we had and insert it into the database and we'd be done. So when we first tested this out with 10 or 20,000 SKUs, it wasn't really a big deal. As we went into the hundreds of thousands and million, this would take absolutely forever. In fact, when we started testing it, it would take more time in the day than there were messages, so we'd actually bleed over into the next day when another file was dropped on us, and so we never actually caught up to be able to insert all this information in there. So we ditched this. We decided that for this specific process, we'd do something different. And there's an interesting feature in SQL Server that not many people know about. It's called bulk insert. Has anyone ever used bulk copy? It's okay, that's awesome. It is magical, especially if you have information you just need to shove in there as quickly as possible. It works absolutely great. There's 3 modes that bulk copy works in. It works on a command line, so you give it a CSV file and it just inserts it into somewhere else. It also works using from SQL Management Studio as well. You can use SQL to do this. And there's the last one where it uses ADO.NET. You can either use a data set, a data table, or a data reader. Now, each of those has its benefits and drawbacks. The big problem with the first two is that if you have to do any sort of transformation on your data, it's really hard to do. Because the command line version, you have to have some like other weird file that describes how to change the data, and then you also have to maintain this like console app. It's not very exciting to do. And then the SQL one is also really weird too. We just immediately eliminated that. And finally, we got to the bulk copy using C#. Now, bulk copy using C# also has its own problems. If you're using a data set or data table, that means you have to load the entire data set into memory and then bulk insert all of that. And so we tried that at first, but loading 1.4 million rows into a data table is like not the best thing to do either. It's just so, it could just completely take over your server with all the memory it needs to do that. And it's also extremely slow at that point. You guys have to load everything into memory. So instead, what we wound up doing was a more streaming method of doing so. So we broke this up into 2 steps, and each of both of these steps are actually managed as part of a single NService Bus Handler. The first step, instead of reading all the lines together and putting it onto a single array, it uses one of the overloads of the file I/O, which reads lines one at a time and then yields them in an IEnumerable. So it reads one line at a time, but only loads that one line in memory at a time. And then you can just use link at that point to split out the individual characters, and then at the second part, you can actually use link to push out into an individual object that it can then be pushed down later to your database. This is also where you can do any sort of transformation you need to do, where it only does it one at a time. Then the second part is, we looked at the API of the SQL bulk copy C# stuff, and like I said, there were 3 different ones. There was a data set, a data table, and the iData reader. Well, the interesting thing about a data reader is that the interface looks very, very similar to IEnumerable, except it's kind of a pull-based model, so it's halfway between an enumerable and an observable. So what we wound up doing was using this one to stream the data from all those different objects we created, and at this point, the bulk writing would take one line of file at a time, and using bulk copy, insert that row into the database. So with this method, we were actually able to get all 1.4 million lines of whatever, still using C# and still having NService Bus manage that process, but it would go through in a matter of seconds as opposed to hours that we saw earlier. So it had a huge, huge improvement in not only just the resources of our server, but it wouldn't take down the entire table all at once. It was just a few seconds to do so. Now, this was for us sort of somewhat of an edge case, but we also still had to push data back out to this other system, where we would export data to that other system. It being AS400, the language it understood the best was still flat files, comma-separated variable sort of thing. And so what we do in this case, originally was something like this. We would have either change data capture, or in this case, the change data capture didn't exist, or it was one of those really expensive checkboxes in SQL Server. And so what we'd wind up doing was just having a flag that said whether this thing changed or not. And so what the process was, it would read from the file and say, okay, select all the things that have been changed. And the exporter would read all those things and write them to the file. And the second step in the process, it would, and while this is reading, something could potentially happen, like something else changed while I was exporting all these things out. And so when I went back in the second time and said, okay, now let's go ahead and clear that flag out, update the people, and set everyone else to not change anymore because I've already exported everyone out. The problem here, of course, is that we're missing this change right here. This person here had been changed, but they never actually made it through. So we had issues where our partners there would say, hey, it looks like you've added people and changed people, but we don't see them coming through. What's going on there? And it took us a while to understand that this is what was going on. We effectively had a dirty read where we'd update someone after reading them, only to realize that, oops, we missed someone in the first place. So we changed this. We changed this and flipped the process, so it was actually reversing the order in which we would figure out who changed and then exported them. Instead of us having a single flag that said, these are the people that were changed, we had this column that was represented an individual export. And so what we would do here was, the very first thing that we would do would be to for everyone that had a null batch ID, which means I hadn't exported them, we would go ahead and say, let's set that batch ID to the next batch number where the batch ID is null. So those two right there that don't have a value, they would get updated to 3, and all is well and good. The next part of the process would be to select those people out whose batch ID matched the one that I just set before. So those are the two that we would pull out, and those are the ones that would get exported. And if someone during that read process got updated, well, it just cleared out their batch ID, and they would go through the very next process. So by flipping these two around to do marking the records to export and then exporting the marked records, we ensured that we never missed anything going on in the future. Now, you can do this with things like change data capture and some other advanced SQL Server features, but we found that that feature is not available in all databases, especially in databases that I don't have a lot of control over or someone doesn't really want to upgrade at all. So this one we found is a nice solution to be able to handle those changes and be able to export them out for other systems to be able to handle. What this looked like in our actual Saga was pretty straightforward. We had a single Saga that would handle those two-step processes. The first thing it would do would be to receive a message to export a file, and it would be given the batch ID that it needs to do. Now, on the previous slide, it was a number, but in reality, that was a GUID, just to make sure there was no possibility of anything overlapping each other. And it would do this two-step process of first marking all the orders to export. And again, hide your eyes, it's just raw ADO.NET. It would go ahead and just set the batch ID to that number where they were all null, and then send a message to itself to say, now go ahead and export those file contents out based on that batch ID. Then the second step in the process was then to, for the next step in the Saga, was to get all the orders processed, write the constants to the file, and then mark my Saga as complete so that the next day when the process ran again, it would go ahead and export those files out. So in this one we were using, in reality I think we were using InPoco or Petapoco, one of those micro ORMs. But the really cool thing about this is it was also able to not keep that connection open for very long by using this yield return. So we were able actually to use yield return as part of reading from the database so that I could still stream that information from the database to the file so that it could go actually much faster and not have to load all of these things into memory every single time. So for us, when we went from, when we introduced NService Bus into the system, we weren't really interested in eliminating those existing integration methods of using files because that AS400 mainframe was not going to go away. Those things were installed in all the stores. There was like 300 stores nationwide, and to try to upgrade that to something else would just be impossible. Or at least cost prohibitive for this purpose anyway. So we said, that's fine, let's go ahead and integrate with that, but we're going to be using NService Bus as a means to help solidify the process and put some control around it and be notified when things fail, but still have that existing process in place so the partners never knew that we were using NService Bus, they just saw the files, but this time the files were just much more correct than they were before. All right, so the next one was an even more interesting one. This is also for the company that I worked, that Ted mentioned, the one that starts with D and ends with ELL. Actually, they know we work for them, so it's whatever. And so when we first got engaged with them, they had gone through this whole Microservice SOA transformation, and surprise, surprise, like completely fouled it up. They read all the books, they did all the things, and made all these different discrete services and used web services as a communication mode between all these different endpoints. They went to go, they did this for like a year and a half, made all the different services, got everything running locally, went to go to a production-like environment, flipped the switch, and then nothing happened. They went to the first page to show information, and then absolutely nothing happened. And what they wound up seeing was that by replacing every single in-process call that there was before with an out-of-process network hop through a web service, they wound up increasing the latency of the website from like 2 to 4 seconds to 5-10 minutes for a single page to come up because network hops are expensive. They never saw this developing locally because locally, all the web services are running on that box, so they never actually had to make a network hop. So that's another lesson to learn. If you're going through this microservice transformation, actually hit services not on your box. Otherwise, everything will look very peachy keen locally. You go to production, and then it won't actually run. So the next thing was to do, okay, Well, this page that I have all this data on, that just shows, in this case, it was just a catalog of information that people searched on, originally would have hundreds and hundreds of API calls. But when we looked right down to it, a lot of that data didn't change over time. So we said, okay, can we go ahead and pre-calculate a lot of this information for search purposes, because the existing databases and APIs really weren't built for search. They were built for just transactional calls. So instead of calling 100 APIs to do something like a search, can't we just store everything in Elasticsearch and have it come out of that? With the caveat that the data is going to be a little stale. So yeah, we could do that. The very first thing they did, though, was because they didn't know what exactly changed, and they didn't know specifically which products they may show, they tried to have an hourly process that would hit the API endpoint to get all the product SKU data and cost data for every single combination of product that was out there, which were like 2 million different SKUs or so. And when they tried that, they again found that there were not enough hours in the day to be able to get all that data updated into their local system. So they said, okay, we'll scale out then. Instead of just having one endpoint hitting that API, let's put 4 machines on there, each with like 16 cores, and use the distributor as a means to try to get much more throughput and data at once, which basically caused an internal denial service attack because they're all trying to hit this one API endpoint, which was the actual bottleneck. So that didn't work. So what they wound up doing was, instead, we were looking at a nightly process of trying to be very intelligent about which data we would update, pulling data from multiple sources, bringing them all together into one single aggregate information that we would store in Elasticsearch to make it much more easy to get out. So we were pulling from multiple sources. Some of these sources are required, some of them weren't. And we also sometimes had data depending on previous sets of information. So I kind of needed to know some SKU data before I got the price data, that sort of thing. And we were able to whittle down, instead of having millions of different SKUs that we'd be worried about, we'd say, what are the top like 10,000 or so, and say, let's just focus on that. So the initial batch of this was to take basically about 10,000 messages and then dump them into a Saga and have that Saga go out and hit all those different endpoints to bring all that data together and then write all that data out to Elasticsearch. Now, it was very important that we had all of the data and not just part of it, because if you searched and you didn't have some of the data, the results will look funny. So we wanted to make sure we had everything before we updated anything. And so what we wound up doing first was, coming from, if you went to yesterday's Saga class, we used an observer kind of Saga that would first have a publisher to say, I want to get the updated data for for a single SKU hitting all these different endpoints. So it'll do one single bus.publish, fan that out into all the different kinds of endpoints and kinds of data I would care about. And once each of those endpoints had the information, they would publish another message that the Saga would handle and then receive that back out and write to the Elasticsearch instance. So conceptually, that worked really great. But we had an issue with this early on, in that there was a lot of contention in Saga creation. Now, this was fixed in 4.x, but also once we saw that the Saga contention issue was fixed, it was also just really slow, because we would have 10,000 messages come into the publisher, and then for every single kind of thing we would need to update, there were that many messages going out as well. In this picture, I have 4 pieces of information. In reality, it was about 12, 8 to 12, depending on what we were doing. So an initial batch of 10,000 messages resulted in not just like 80,000 messages, but 160,000 messages, all coming back into this initial Saga. And so we'd have another bottleneck there where we'd run into. So our next step was to say, let's see if we can just have the Saga then publish things out, publish out the messages, and have everything come back in. This helped solve the Saga contention problem, but again, it just resulted in way too much queue contention on that Saga, because everything was dealing with all that data. Okay, so next step was, let's try to scale out our Saga. Instead of having the one single endpoint receiving 160,000 messages, what if we split out all the different components so that when one single component was done, it would go back to a separate queue for that individual response that would update that common Saga data. Now, the Saga contention problem had been fixed, but this problem had another issue. When it fanned out and came back in, they would go back to individual queues. But when it came to actually go ahead and deploy this, it was very, very difficult to deploy. It was very complicated because we had to really make sure that all the routing between all these things was correct. If we messed up any of the routing, we could potentially lose a message. And everyone here has actually gone through the process of trying to do this with Sagas. It's theoretically possible, but in practice, it can be pretty difficult to actually do this. With this, I only had 4 endpoints in this picture, but with 8, 10, 12, it was really hard to manage in production. Okay. So we basically said, let's throw out the whole pub-sub model. Let's see if we can establish some order here and then say, let's go to a controller style Saga so that instead of me having like all these messages coming in at once and then having a lot of contention, I control the order in which things happen. So I would send a message to my Saga. That would kick a message off to the price endpoint. It would get the updated price. That would go to the catalog data, get the updated catalog information, get the content, which would be like description and name, go out to there, and then finally go out to the options. And for every single one, it would do this. When all those were complete, it would go ahead and finish. This is slow, very, very slow. Well, why is it slow? Well, in this case, when I have a sequential process, I have 10,000 messages dropping on my Saga all at once. 10,000 messages go out to the price endpoint, and then 10,000 replies come back to the Saga. But they go back to the same queue that all the other messages are sitting in. So they actually go to the back of the line, waiting for all the other ones to finish before I can even go on to step 2. So step 2 couldn't start until all of step 1 was done. Step 3 couldn't start until all of step 2 was done, step 4, step 5, step 6, step 7 to 8. It was kind of a depressing thing to see this because you're like, oh man, it's much easier to control, but now I have everything going back to the one queue. So, let's go to multiple queues then. So my controller Saga will send out to the price one. The price one will reply back to the price endpoint. Price endpoint will say, start step 2. Catalog will say, okay, it's done, go to step 2, step 3, step 4, and finally we're done. This is actually even more difficult to manage than the pub-sub version because I have to be very explicit about where all these endpoints are replying back to and what the next step should be. And if a new step showed up somewhere in the middle there, like we just gave up. We're like, okay, clearly this is absolutely insane. And it was also very slow because, again, I have so many messages getting generated here. So this is where we took a step back and said, clearly this is not a new problem in the world. People have figured this out. And so I wound up going back and trying to figure out how people in the real world try to deal with these sort of situations where I have a set of things that need to happen, and only when all of them are done can I then go on to the next step. And so it's very similar to what we found in something like a fast food restaurant, where whenever you go order at a place like McDonald's, this actually publishes a message out to a bunch of different stations that all are then responsible for doing those own individual set of work. And once each individual step is done, it comes back and goes out. In this case, a tray or something contains all the items when they're done. And when all those items are complete, then I actually go and notify a customer, hey, your order's done, here you go. Now this works really well for scales of like human sort of behaviors where 10,000 people don't just show up at McDonald's or whatever all at once. It's very piecemeal and very easy to manage. But I do have an issue that there is still some contention around this individual tray. And you may notice this sometimes if you go to a fast food restaurant and there's a lot of people there. Like when this food is done, you'll actually see the person like go down the line and be like, okay, where's my tray? Where's my tray? Oh, here it is. And every single time they come back to the tray, they have to check the ingredients to say, is everything on that Saga done? And then I can put it out there. This is why that you can still process a lot of orders this way because you're doing things in parallel, but you're more likely to mess things up because it's a human checking the list of items. So this is why at McDonald's you always check your food, right? Because they may have screwed something up. This is not how all restaurants work, though. You see other ones that are more like our process, which it's a series of steps all done in sequence. So if you go to Subway, for example, the first thing you do is you place an order at the register, and you actually, with that person you place the order, you go down the line with that person with every single step. So I walk to the next step. They ask me what they want on my sandwich, what dressing I want, what vegetables, everything, all the way until it's completely packed and done, and then they give it to me. So if you look at this and try to figure out like where is actually the Saga in this picture, there isn't a Saga. There's no central coordinator who is who was figuring out what to do next, how to make things go down the line. Instead, it's more of like an assembly line where something just goes through a process. And so there's actually a pattern that exists for this already out in the real world, and it's called a routing slip. And the idea behind this is if I need to route something through a series of steps, and that series of steps can potentially change, instead of me having it built into some central coordinator, I can write the steps down on a piece of paper and have each step look to see where the next step is and have it go down the line. Now, I got this description out of the Enterprise Integration Patterns book, which not surprisingly is what we're talking about today. It's that book that's like 900 pages that you can use to throw at people if they're robbing you or to make yourself look smart. If you ever try to build a queuing system without InServiceBus, you'll find that you have to implement about 2/3 or 3/4 of the patterns in that book to make a system similar to InServiceBus. And that's where I got this, this individual pattern here. So what this looks like is instead of me having a ton of messages going out through all the different pieces, instead of what I do is I have a series of sequential steps that when I kick the message off, I tell it exactly the sequence of steps I want it to go to. So the message as it flows through the system goes from the initiator to the first endpoint. The first endpoint does its work and then just looks at the routing slip information to know where to send it to it next. So it forwards the message directly to the very next step. It gets to the catalog endpoint, gets to the content endpoint, goes to the options, and of course 8 to 12, however many there were, and then finally it finishes and goes to the last endpoint and then actually writes that information to the database. So one of the advantages to this approach is that, one, I don't actually have to have a central coordinator to manage this activity. So that Saga entity that I kept writing to the database, there's actually no entity that manages the state of this process. A message just flows directly through the system as it would any sort of assembly line. And I actually picture an assembly line in my head. These steps in an assembly line are more or less fixed, and you have things just sort of flowing through the process. The time for any one piece to finish is just the time for all of the individual components to finish, irrespective of the other amount of messages in the queues. So the first one going through the process flows straight through and finishes, regardless of how many others are actually going to be in there. So we can actually get updated data into our search endpoint much more quickly because I'm not having to worry about everything being done. I'm worrying about just one individual component flowing through the system. This also let us add additional steps pretty easily because it was the initiator that defined the list of endpoints to route to, so I don't have to worry about if a new system comes online, no one individual downstream endpoint knows about it. They're always just doing a simple forward on to the next individual step. Now the downside of this, of course, is it's very hard to know like where something is in the process. If you want to know, for example, on a manufacturing floor, has anyone here actually gone to a manufacturing facility and like just looked and seen? It's absolutely crazy because you read all those lean books and whatnot, and you can actually see it in action. But for someone to actually know like what's going on with my manufacturing floor, with my assembly line, you have to go visually inspect to see where the bottlenecks are. So the downside of this process is it's much more difficult to visually inspect to see where things are in the pipeline because it's just messages sitting in queues. With our Saga, we actually had a central point I could go query to see how many things are finished, how long did it take for them to finish. So in this case, we had to add more infrastructure to publish messages to have a reporting endpoint tell us where things were in the process or something got hung up somewhere. But it did allow for at least the main business concern of search data getting updated to be much more quickly and easily done. With this one, we saw somewhere along the lines of 10 to 20x throughput improvement by not having a central coordinator manage this process. Much less I/O because I only have n number of messages flowing the system as opposed to n squared or whatever it was before, and whatever crazy thing it was before. Okay, so one of the morals of that story, though, is don't use a distributor against a web service because that's just crazy talk. And then the other moral of the story was we really wanted to make sure that we had a good experience for the end user. And for us, that meant we did have to duplicate some data in a very specific store, but using a service bus, it allowed us to still manage all those different endpoints, still preserve the existing API structure they spent a year and a half creating, but also still provide that good end user experience. Okay, my last example is more mainframe madness with store procedure explosions. Now, a lot of the techniques I've shown today assume you have some control over the database. I can add a column to say it's changed or not. I can add another table. I can do whatever. But sometimes I have absolutely zero control over the schema or information in that database. And this is one of those examples. We were migrating one of our clients from an existing mainframe over to an actual database and real .NET application. So the existing application was one of those green screen applications. They would put stuff into some COBOL magical database where all the logic and all the behavior existed. It wasn't in store procedures, but it might as well been. It was like those 1,000-line files. I don't remember the COBOL names, but it was like sentences and words or something. I forget exactly. Procedures and I don't know. And it was all embedded inside that database. And we couldn't change it because that was still being used in production today. So we looked at this and said, well, what we can do is we can stand up an app to the side, and we will gradually transition slices of functionality into this new .NET app and have some sort of process get the information out of this one and into the new SQL Server database. Now, this one I think was trying to do bidirectional updates, which is also a very, very hard thing to do. I wouldn't recommend if you can avoid it. Ideally, it's this like one-way scenario where someone is using this .NET app and we have some sort of bridge back into COBOL. But again, if you have an existing really old legacy system, sometimes that's just not possible. So the big question was, how do we get this information out of this COBOL mainframe into SQL Server, knowing that someone is potentially going back and forth between these applications? So the data has to be updated pretty quickly. We can't just do a nightly bulk export and say, here's all the data from yesterday. This is actually a transactional system, so they needed the data within sometimes seconds to be able to see it in this updated system as we were transitioning over. So the initial thing we did was go to the customer and say, okay, what can we do with this database? Can we add triggers? Yes, we can. Okay, so very similar to that awesome slide that Andreas had of a trigger in there. I won't actually show the trigger because the mainframe code was horrible. Even more horrible was having an NService Bus Handler in the middle here that on every single trigger fire, we would just go ahead and say, okay, something updated. Go ahead and update the thing on SQL Server. So we thought this would work really well. When we first did our prototyping, it worked fantastically. Someone would do an update, and seconds later, we would see it in the front-end app. But then we added 10 users, and it would take minutes for us to see the update. We added 100 users, and it would be the next day before those things showed up. And the reason being is that those triggers, while the front-end user may have done one thing, that actually may have resulted in 100 triggers firing, which meant 100 messages getting sent to an NService Bus Handler, which meant 100 updates to SQL Server, finally going back to the being shown in the .NET app. So if I have 10 users, it was 1,000 messages, or even more exponential up than that. So our NService Bus Handler just couldn't keep up because it was getting inundated with all these trigger messages. So again, this was very, very slow. And actually reminded me a lot of those pictures of the particle accelerators, where you have 2 particles coming in and 1,000 things coming out. That's what these old legacy apps were doing. Is one individual button click on the screen would result in 1,000 things happening that we had no real understanding of. Sure, there's quarks and gluons, but every once in a while some weird particle would show up. We're how did that change that? And we have to worry about that as well. So the only way we could really reduce the number of messages down was to try to put some sort of buffer in all those things coming out. We try to be smart at first to say, I know when they approve an invoice that it's going to go do this thing over here, but when we, in practice, it looked more like this, where it did 10 other things we didn't know it was going to do, and so there's no prediction about exactly all the things that could change as a result of one single thing the person did in the front end. So what we tried to do instead was just have our NService Bus endpoints kind of slow their roll and not be so happy and trigger happy pushing messages out to and updates out to the SQL Server. So in this case, our idea was one message coming out, 100 updates going into NService Bus, and then NService Bus says slow down and only sends one update out to SQL Server, so it's not just killing our SQL Server with updates. But because we didn't really know how many updates there may or may not be, we had to be really careful about not discarding updates or forgetting something along the process. So we actually removed most of the understanding of what was actually magical about this and just said, let's just try to slow a roll and batch up updates into our SQL Server. So that's exactly what we did. And our Saga here It did two things. First, it was notified that a legacy product was updated, and it would partition that data in the Saga by product ID. So I basically look at the primary key of the database and say, I'm going to have a unique Saga for each row that I get updates out of from the original server. Then handling these actual messages, handling an individual legacy product updated, I would just capture the correlation ID and do this request timeout. So instead of me trying to be smart about knowing exactly what changed, I would just wait a little bit. In this case, we would wait about 5 seconds for us to actually send the update out. But we'd be smart about it so that if I've already requested a timeout, I wouldn't request another one. This would ensure that I didn't have a cascade of updates coming down. I would just basically batch up for about 5 seconds, wait, send all those updates out, and if something came in after that, I would start another 5-second buffer as well. So when our timeout came in after 5 seconds, then we'd go ahead and send the message out to say, okay, go actually update this data based on all the data you see and mark as complete so that the next product update coming in will go ahead and update itself as well. The mark as complete was important for us because we wanted to make sure the next one coming in kicked off a new 5-second delay. So if the 5-second delay worked and 30 minutes later another 5-second delay came in, that was fine. We didn't have to have a periodic process, just keep polling and polling and polling. So this wound up being much more intelligent than that first mark, where I null out a batch ID, because I can gather up a set of changes all at once to be able to be sent out, but I don't have to have the overhead of adding a single Saga for every single product row that exists. I can just, as things update, I'll go ahead and push those changes out. So we looked at updating from files. We looked at updating to files. We looked at using different messaging patterns as a means to tie together microservice APIs to build up an aggregate data source for our front ends to use. And finally, we looked at bridging across to legacy databases through a very non-intrusive way to be able to effectively update our new data source, a new app coming up in the future. So we have some time for questions, about 3 minutes. I know lunch is coming up here, so we'll try to keep it to 30 minutes of questions, if that's okay. I'm just kidding. You can, again, find everything here on my GitHub and everything. So thank you very much. Let's see what questions anyone has. Yes? Okay, so the question is, what if I had like 1 million of these things show up here? So in that case, we are effectively able to scale out our Saga, so we can have, because it's one endpoint, I can have lots of different threads being able to handle all those different updates. And in this case as well, we're not really worried about one individual product screwing up someone else, because when timeout comes back in, I can actually have this one go to a separate endpoint, so it's not in contention with this message up here. Yes? No, we're only doing one product ID at a time. So the question was, am I concerned about a collection of products or just one product at a time? The triggers didn't work that way. The triggers sent out updates for every single row. So we weren't able to really, we just would get random trigger messages coming in. And so we can only reason about things one product ID at a time. And we didn't want to have to extend out and know at 0 seconds, this product ID got updated, but at 4.9, this one did, and so we're going to potentially miss something from the next one that happens. So we try to really bake it down to the activities the user were doing, which is basically still one row at a time.
So the message for product ID is fine because you're getting one product updated at a time.
Yes.
But the Saga is waiting for 5 seconds to build up a batch of products.
A batch of updates from that one product. So what happened would be I'd have a dozen updates for that single row, and it would trigger, and I would hit 12 updates for that one single product when I really just wanted the product was updated, not the product was updated 12 times.
I guess you probably use that for job tables if the product has product price table or something, rather than the user updating the same product in 5 tables instead of sending 5 changes.
Yeah, so the question was, what do I do when I have, a lot of times we'll have dependent data. And so we would make our Sagas a little bit more intelligent about responding to parent and child updates, so I could batch them all together and push them out so there's not foreign key constraint violations. Or we just turn the constraints off. Yeah, Daniel. Yes, we did. But we get reliability out of it in the process, and we have to buy BizTalk, so bonus. All right, it's lunchtime. Thank you very much. We'll see you around.